we finished talking about the solar system and we started talking about exoplanets and life elsewhere in the universe. And a lot of the information that we got from all of those astronomical bodies is from studying the light that we get from those sources. So today we're going to talk about optics, which is how we can study light and instruments that we can use to better understand light. And then on Friday, we'll talk about how we use optics to design systems like telescopes, which are what we use for astronomy. Today, we're going to talk about optics, which is the study of mirrors and lenses. So just to review, we've talked about light and matter interacting before. So which of these is not a way that light and matter interact with each other? Yeah, so emission is matter producing a photon, absorption is matter taking in a photon, reflections are photons bouncing off of matter, and then refraction is a less clean bouncing of light off of matter. So remission is the one that is not dealing with light and matter. That's what you have if your cancer goes away. So today we're going to talk about lenses and mirrors. We'll start with lenses and then we'll move on to mirrors. And we're going to see how light interacts with these objects. The technique that we're going to use for thinking about how light is interacting with these objects is called ray tracing. And so you'll have some photon or some light ray that's going to hit your surface, and then depending on the characteristic of that surface, whether it's a mirror or a lens, the ray that you draw for what happens after it interacts with the object will be different. So in the case of this flat mirror, you have an incident ray coming in, and then you have a reflected ray coming out, and the angle is going to be the same for the incident ray and for the reflected ray. So you draw a dotted line perpendicular to your surface, and then whatever angle you measure for your incident ray will be the same angle for your reflected ray. So this is how refraction is a bit different than reflection. So the light ray is still going to bounce off of the surface at a equal angle that it comes in at. So the black lines, you're drawing a line that's still perpendicular to your surface. The only difference now is that instead of your surface being nice and flat and uniform, it's kind of bumpy, and so when you draw your rays, you see that they're not all uniform, they kind of spread out in these various directions. So the physics for one individual light ray is the same. It's going to hit the surface and bounce off at an equal and opposite angle, but because the surface is now rough, when you add up the effect of several different light rays hitting it, you get refraction instead of reflection, which you get for a nice smooth surface. The way that we see the effect of light interacting with a mirror or a lens is by looking at what image it produces. So if you look at this person's looking into a mirror, if you draw a line going from the top of their head to the mirror and then back into their eye, so that's how they can see themselves in the mirror. The way our vision works is we will trace this, the ray that's coming into our eye, we'll trace that backwards, and then where that ray goes behind the mirror and the distance behind the mirror it goes will be related to the curvature of the mirror that we'll talk about later. But so where that dotted line goes behind the mirror is where an image will be produced. So if you look at yourself in a mirror, you don't see yourself directly on the surface of the mirror, you see yourself somewhere behind the mirror. So if the mirror was mounted on a wall, the image that you would see would make it look like your image is behind the wall. You're not seeing your image directly on the surface of the mirror. And so you can play the same game with a ray coming from her foot. So the light coming from her foot is going to hit the bottom of the mirror and then get reflected into her eye. And then again, we trace that backwards, and so she would see her foot behind the mirror somewhere at this angle. And so something else that you should notice is that you don't necessarily need a mirror that's as big as you are to see your whole body reflected inside of it. But you do have to pay attention to your distance from the mirror. If she got closer to the mirror, then she would no longer be able to see her full body in the image. So the two types of objects that we'll talk about that interact with light in useful ways for us are lenses and mirrors. So lenses allow light to pass through them. You can think about the lenses in your glasses. And then mirrors will reflect the light instead of letting it pass through them. And these are useful for looking at seeing what you look like, or as we'll see in astronomy, building telescopes. Vocab words that we will use when we're discussing lenses and mirrors are focal point and focal length. So the focal point are where all of the light rays converge for a given mirror or lens. And then the focal length is the distance from that lens or mirror to the focal point. We'll start with lenses first. So there's two types of lenses. There are convex lenses, or they're sometimes called converging lenses. And then there are concave lenses, which are called diverging lenses. And so these lines are the general shape that you would have pieces of glass in order to achieve a convex or a concave lens. So the convex lenses curve outwards, and the concave lenses curve inwards. The mnemonic device for remembering concave is you can think of the curvature as what you would expect for like the opening of a cave. So it's going to curve inwards, so you could go into it for it to be a cave. And the converging and diverging are going to describe what the light rays do when they interact with these lenses. So let's look at a convex or converging lens first. So I'll draw it on the board so you can see each step of the process. So we have our lens. If we look at how one light ray will interact with this lens, due to the curvature of the lens, the light is not going to pass straight through the lens. Instead, it's going to be curved or bent like this. So this is the path that light ray 1 will take through the lens. If we have a light ray that hits right in the middle of the lens, now there's not really a curvature at this point. It's basically hitting it at a 90-degree angle, and so it's not going to be bent at all. So light ray 2 is just going to pass straight through the lens and not get bent. Then for light ray 3, again, now it's hitting a more curved part of the lens, and so it's going to be bent after it passes through the lens and take a path that looks like this. So where all of these light rays intersect is called the focal point. And the distance from the lens to the focal point is called the focal length. And different curvatures of lenses will have different focal lengths. So I just drew one example of a curved lens, but you could imagine one that has more curvature or one that has less curvature. And the degree of curvature will determine the focal length of that lens. And for some of the equations that we'll see later, this focal length we're going to write as the variable lowercase f. And so the reason that this is a converging lens is we take a bunch of parallel light rays, and when they interact with the lens, they will converge behind the lens. You can also do this process backwards. So instead of having parallel light rays that are incoming, you could start with, say, an object that you're looking at through the lens. So you could have an object here at the focal point, and then light from that object will pass through the lens, and then on the other side of the lens it would be, the light would be spread out and it would be parallel. So you can have, whenever you make a ray tracing diagram like this, they're always reversible. So the lines themselves don't change, just the direction of the arrows change. So a convex or converging lens can take parallel light rays and make them converge, or it can take this single point of light, and after it hits the lens, it can make that light become parallel. So let's do the same thing for a diverging lens. Okay, now because of the geometry of this lens, when this light ray hits, it's not going to be bent downwards, it's instead going to be bent upwards. 2 is hitting at a perpendicular angle, so it's going to pass straight through. And then 3, again, it will, when it interacts with the lens, it'll get bent, and it'll get bent downward. So now the diverging lens is taking these parallel light rays, and after interacting with the lens, it's spreading them out. So on the right side of the lens, there's no focal point because there's no place where all of these rays intersect with each other. So this is where we have to use the kind of backward ray tracing. So if we take this line, and so on this side of the lens, if you are looking at this light coming to you, you don't trace this line back to where it came from, you just trace it straight back along this ray. And then 2 is just straight through, so we'll trace that one straight back. And then again for line 3, we're going to trace it back along this angle. And so from this side, we would see these 1, 2, and 3 converging on this side of the lens. So for a diverging lens, the focal point is actually on the same side as the parallel incoming rays. So this is our focal point, and the distance from the lens to the focal point is still just the focal length. And then just like the converging lens, these rays are also, you can reverse the direction. So if you had on the right side, if you had your light rays all spread out and converging onto this lens, it would take those rays and turn them into parallel rays on the other side. So if you're someone that wears glasses or contact lenses, then you'll know that not all glasses are the same. And so the power of a lens, or how much light, the amount of light that it bends, is called its power. For a convex lens, the power is positive, and for a concave lens, the power is negative. And the power of a lens is related to its focal length. So you take 1 divided by the focal length, and you get the power of your lens. So the unit that is used especially for optometry are diopters. And so that'll be the number of your eyeglasses prescription. So mine is pretty bad, so I'm at like -5 or 6 for my diopters. Okay, so now what do we do with these lenses? So we can take the light we can take light interacting with the lens, but how do we do something useful with that light? Let's take an object. So let's say we're looking at a tree. Some light will be coming off of the tree, interacting with our lens. And then after interacting with the lens, the light will be bent in the ways that we saw before. And now, depending on where you place yourself after this lens will determine what kind of image you will see. So if we trace these lines past the focal point, so let's say you set up this lens in between you and this tree, and you look through the lens on the right side of the focal point, what you would see is, if we trace, let's label the rays, if we trace ray 3, that would be this one, and eventually it would end up on the top of your image. And then if we trace ray 1, that would end up at the bottom of your image. So if you're looking at your, if you're past the focal point of your lens, you would actually see an upside down image. You could also you can look through your lens and be closer than the focal point, and then you would see the object right side up. So when you're designing optical systems, where you put your lens and how far you are from your focal point will change what kind of image you're seeing. Let's just focus on one image for now. And there's an equation that will let us calculate where your image will form based on the object and the lens. So this is our object. And so the distance between the lens and the object is the object distance, or d sub O. Then the distance from the lens to the focal point is f. And that's just a property of the lens itself. And then where this image forms is d sub I, which is the image distance. And so using these three variables, using two of the variables, we can calculate the third. So that formula looks like this. 1 over the object distance plus 1 over the image distance equals 1 over the focal length. So we'll keep that equation in mind, and we'll learn a couple other equations that deal with optics, and those will form kind of the basis for any calculations that we need to do. And then we can do the same thing for the diverging lens. So again, we'll have our tree as our image. If we draw where the light rays go on the right side of the lens, they will start diverging. And so if you are looking through the lens at this tree, the way our vision works is we trace ray 1 back to where it looks like it came from, and so we would see this tree on the same side as the object, so the image is on the same side as the object, and we're seeing it right side up based on the orientation that we have. So this is one of the ways that eyeglasses or contact lenses work. So if your eyes are not quite working correctly, then the light coming into your eye might be diverging too much before it gets to your retina. And so you can have your eyeglasses refocus the light so that you're seeing an image that is in focus and right side up rather than seeing a blurry image. And the same equation applies to both the converging and the diverging lenses. So this is kind of a big table. You don't really need to memorize this, but it just helps you to keep some information straight. So there are different types of images that can form when you use lenses. For this class, we don't necessarily need to know the difference between a real and a virtual image. The real image is basically one that could exist in real life, and a virtual image is one that could not exist in real life. The different cases, so you have positive focal length, meaning case 1 and case 2 are for converging lenses. Diverging lens is negative focal length. So diverging lenses will always produce virtual images. They'll always have an image distance that's negative, meaning it's on the left side of the same side of the lens as the object. And as we saw in our image, so this M is magnification. We'll talk about that in a little bit. The tree on the left side of the lens was smaller than the original tree. So the magnification is less than 1, meaning it made the object smaller. For case 2, this is a converging lens, positive focal length. It still produces a virtual image because the image distance is negative, meaning it's formed on the same side as the object. So your virtual images will form on the same side as the object, and your real images will form on the opposite side of the lens as the object. But again, that's perhaps beyond the scope of this class. Okay, so that was lenses. Now let's talk about mirrors instead. So we'll start with a concave mirror. So we have our light rays coming in. It's a concave mirror, so we draw our curve like this. Now for a mirror, the light rays are reflected. So if we draw our 90-degree angle at each of these points, the incoming angle has to be equal to the outgoing angle. So you might get something like this. This one is just hitting straight on, so its reflected angle would be like that. And then this one's coming in at this angle, so it'll get reflected kind of like this. So we get our light rays intersecting here. And so where your light rays intersect is your focal point. And then the distance from the mirror to the focal point is the focal length, f. So if you have curved mirrors, then you'll have focal points and focal lengths. We'll need to do the same kind of drawing for a convex mirror. So we'll have our light rays coming in. Now we have a convex mirror. If we draw our -90-degree angle coming off of the surface, now the equal and opposite angle would look something like this. This one will still just bounce straight back, and this one will go off this way. So now on the left side of the mirror, there's not a place where all of these rays will come together. So instead, we have to continue the rays behind the mirror, and then you get a place back here where all of your rays converge, called the focal point. And the distance from the mirror to the focal point is the focal length. So for the convex mirror, because the light rays spread out after they hit it, that's a diverging mirror. And then for the concave mirror, because the light rays come together after interacting with the mirror, that's a converging mirror. So some of the practical applications that you've probably seen for these types of mirrors. So for concave, if you have like a makeup or beauty mirror that makes your face look bigger so you can see yourself in better detail, that's a concave mirror. And at like grocery stores and gas stations, the mirror that's up in the ceiling that lets you see around corners, that's a convex or diverging mirror. So there's different kinds of everyday applications that you'll see these different types of mirrors used in. You're probably most familiar with a flat mirror. So if you have some object in a flat mirror, the light coming from the object will bounce off the mirror and enter your eye, and then you'll use your backwards ray tracing to see the image back behind the mirror. For the flat mirror, the object distance and the image distance are going to be the same distance. But we need to use the ray tracing to see where the image, or what the image will look like in the mirror. Just a little chart to remember what concave and convex goes with when we're thinking about mirrors and lenses. For mirrors, the concave mirror is a converging, but for lenses, the concave lens is diverging. For convex mirrors, that's the diverging one, but for convex lenses, that's the converging one. So the way I do it is I just remember one of them. So say you remember what lenses are, and then for mirrors, it's just the opposite. So concave lenses, I know those are diverging, so concave mirrors have to be converging. Okay, one of the ways that lenses and mirrors are useful is that they can magnify objects. So they can make the image of the object be bigger than the actual object itself. So if you think about magnifying glasses that a detective might use, they're able to see a small thing in better detail because they're magnifying the object and seeing an image that's much bigger than the original object. So to calculate the magnification that a lens or mirror provides, you just take the height or the size of the image and divide it by the height of the original object. It turns out that the image distance and the object distance are also another way to figure out magnification. So if you are trying to magnify an object to a certain degree, you can place your object a certain distance away from your lens to get a desired magnification. For astronomy purposes, the bonus for magnification is when we're going to talk about telescopes. So telescopes allow us to see very far away things in better detail than we can see with our eye. And part of the reason that is effective is because we can magnify the object. Outside of astronomy, this is also how microscopes work. So if you're more of a biology person, then microscopes magnify things like cells that we can actually see with our eye through the microscope. So if we combine these three equations together, the two different ways to calculate magnification, and then the one that we saw earlier relating the object distance, image distance, and focal length, those three equations together are called the thin lens equations. And these apply to lenses and mirrors. So which of the following lenses and mirrors produce converging light rays? So the convex lens produces the converging rays, and therefore the concave mirror has to produce the converging rays for mirrors. There's some other interesting things that you can do with, say, a piece of glass interacting with light. One of those is dispersion. So if I take a prism and I shine white light into the prism on one side, on the other side I can get a rainbow of colors coming out. So the white light is actually made out of all of these different colors, and because the index of refraction of the glass is different than the air, and the speed of light for the different colors will actually change inside of the prism, you get different colors traveling at different rates, and so they basically they'll bend by different amounts as they travel through the prism. So you can get a spread of colors out of a combination of colors. So combination of colors on one side, you spread out the colors on the other side. And this is very important. So we talked about spectroscopy earlier. This is a way that you can study the spectrum of light. You need to spread out all of the light that's together so you can study the individual colors or wavelengths of light. So the index of refraction is a measure of how light travels through that material. Different materials having different indices of refraction are what cause, for example, a pencil to appear like it's broken when it's sitting in a glass of water. So the index of refraction of the water is different than the index of refraction of the air, and so you get the basically the light traveling differently through the air and the water, giving this kind of broken appearance. And so the relationship between the index of refraction and the angle that the light is bent is given by Snell's law. And one of the interesting consequences of Snell's law is total internal reflection. So if we take Snell's law and we set one of the angles equal to 90 degrees, then we can solve this equation for the angle and index of refraction that we need to basically not be able to see out of whatever medium we're in. So if we take this picture on the right, we have a person in a swimming pool, they're in water, and so that'll be one of the indices of refraction for water. Then above the pool, there's air, so that'll be another index of refraction. There will be an angle that they're looking out of the pool such that they won't be able to see out of the pool anymore. And so to see an example of that, we have this picture. So you can see the bottom of the pool at the bottom of the image, and then as you're looking up, there's a small region where you can actually see out of the pool, but then for most of the length of the pool, you cannot see out of the pool. So this is the total internal reflection. This has some applications in things like fiber optic cables. There's total internal reflection in those. And I think it's just a neat consequence of some of these optical things that we've discussed. And so what happens if you put multiple lenses and mirrors together? You can make things like microscopes and telescopes, and for an astronomy class, we'll talk about telescopes next time.